Okay, guys. So here we go. All right. So problem number 2 has this dart being launched. It hits a pendulum. The pendulum swings up. It asks you some questions. All right. So there's a lot going on here. So in my mind, there are 3 parts to the problem, right? There's the dart being launched through the air. So sort of what unit is that? This should be easy. What? Kinematics, projectiles, right? Everybody good with that? Guys, come back, please. All right. Then the dart hits a wooden block. What should we be thinking about now? Conservation of momentum. Anytime you're dealing with a problem that is a collision between 2 objects, you should automatically go to conservation of momentum. Good? Then, after the collision, the pendulum swings up. Now what should we be thinking about? Conservation of energy, right? Because as the pendulum swings up, you're going to lose kinetic energy but gain gravitational potential energy. Good? So there's a lot going on here. All right? So, part A says determine the speed of the dart just before it strikes the block. So if you read through the text of the problem, it tells you that at the instant the dart hits the block, it's at the peak of its path. Why is that important? All of the motion is horizontal, right? So question A is really just asking you, what's the horizontal velocity of the dart, right? And what should be true about the horizontal velocity of any projectile, you guys? Constant. Okay? So here's the deal. The dart is launched with an initial velocity of 10 meters a second at an angle of 30 degrees. So there's a horizontal velocity and an initial vertical velocity. Use a little bit of trigonometry, figure these out. The Vx turns out to be 8.66 meters a second. The Vy is 5 meters a second. Any problems with that? So that's part A. All right. One second. Oh, darn it. I know, creative things. I got all kinds of things. All right. Okay. All right. So is everybody good with that? All right. Part B says calculate the horizontal distance between the launching point of the dart and a point on the floor directly below the block. So you're looking for the distance that it goes horizontally before making contact with the dart. So what other thing do we need to know? The time to get to the top, right? So, thoughts about how to figure that out, you guys? Good. So at the top, here's what we know. Our Vfy is 0. We already figured out our Viy was 5 meters a second. Since 5 is easily divisible by 10, I'm going to use acceleration of gravity to be negative 10 meters a second squared and find my time. To get half a second. Follow? So then you just do delta x times t. So d equals, I'm sorry, Vx times t. So 5 times, why am I dumb? 8.66. Oh, thank you. 8.66 was our Vx. Thank you.
How big are the 8.66?
Not at all.
Okay.
Yeah, the question was how picky are they on sig figs? Not, is the answer. So my strong recommendation to you is keep, as you're doing your, well, A, keep numbers in your calculator, and then at the end just round off to 3 digits and call it good. Cool? All right. Any problems?
How, if you got 4.416.
Did you use 9.8 instead of 10?
I did 10.
There you go.
No, it's right.
Yeah, so that's fine. All right, everybody good on this? Okay, my recommendation would be to use 10 just because you can do some mental math a little quicker. But if you're so ingrained into using 9.8 and you're worried you might like switch back by accident, then you know what I mean. Just make sure you're consistent. That's the most important thing. All right, is everybody good? All right, moving on. Part D. Oh, wait a minute. Oh, I skipped part C. Or is it just out of order? No, I skipped it. Darn it. Okay, part C says to calculate. Darn it.
It says the speed of the block just after the dart.
Yeah, right. So part C wants to know the speed of the block right after the dart hits it, right? So what should I be thinking about here, you guys? Conservation of momentum, right? So you're just going to go the mass of the dart times the velocity of the dart initially plus the mass of the block times the velocity of the block initially equals the mass of the dart times the velocity of the dart final plus the mass of the block times the velocity of the block final. Cool? And so let's see, the mass of the dart is it 0.01 or 0.02? 0.02 times, we just found the velocity, it was 8.66, right? Plus 0 equals, the combined mass is going to be what, 0.12?
Yep.
That is VF. We'll solve for VF. Cool? And so you get a number that I've written down on a piece of paper, which is not currently in front of me. Where did I put it? 0.14, is that right? Oh, it's in my folder. Crazy place to put it in an organized spot with all of my other reviews. Okay, so yeah. So your VF turns out to be 1.44. Any problems? All right. So now part D says calculate the angle through which the dart and the block on the spring will rise before momentarily coming to rest. So the idea is immediately after the collision, I've got all this velocity, which I can think of as kinetic energy, right? As it swings up, we lose kinetic energy but gain GPE, right? So if I call this a height of 0, then I can just set this KE equal to this GPE. Yes? Do I need to go through the calculations there to show you how you get the height? I'm happy to if people want me to. Speak up. Okay, so when you find that height, this height ends up being 0.104 meters. Cool? Sorry, that green is bad. I won't use it again. So I know that this guy here is 1.2 meters. Since this whole orange thing is 1.2 meters, that means that this must be 1.2 minus the 0.104, right? So that's 1.096. And now I can use a little bit of trigonometry and find that angle, since this is the right angle. And it turns out to, I got 24 degrees. I didn't even check my answer against the thing. I didn't get a chance. Yeah.
I got it right, I got the speed right in A, but I accidentally used the distance instead of the speed. So since I use it consistently throughout, would I still get that?
I believe that is correct. I think that they would write, yes. Like as long as you correctly used that incorrect number throughout the rest of it, I believe they would give you all the credit minus 1 for that one mistake.
Okay.
I believe.
Hope so.
Although that only affects that one problem, right? Oh, wait. Oh, I see what you're saying. So up in part C, you switched it?
Yeah, I used the distance.
The 4.3 instead of the 8.6. Gotcha. Which messed up your velocity. I understand. Yes. Then what you said is correct. Okay. Everybody good up through part D? Did I do that too quickly? Okay. Part E says, how long will it be? Well, how is it worded, actually? Let's see. Part E, the block then continues to swing as a simple pendulum. Calculate the time between when the dart collides with the block and when the block first returns to its original position. So you're looking for the time for the block to go up and come back down. Tell me something useful. Isn't that half of a period? Right? Because a full period would be a full swing there and a full swing back, right? This is half of that, right? So the time we're looking for is half of the period, which is 1/2 of 2 pi root L over G. and solve it. Cool? All right, and then finally, F. In a second experiment, a dart with more mass is launched at the same speed and angle. The dart collides with it and sticks to the block. Is it going to go to a bigger angle, smaller angle, or same angle? Bigger. Good. Somebody give me a simple justification for why. Sure, what do you got?
You have more KE at the top point, right? So then it will all be converted into
More. What do you mean when you say more KE at the top point?
As in comparison to the other one, KE is 1/2 mv squared. So as the mass increases, the kinetic energy increases.
Gotcha. I think you need to be, and to be fair, I haven't looked at the written out answer. I think you got to be careful though, because the collision is inelastic, so you lose some energy during the collision. So I think you need to make a two-step argument. Okay. So what do you got?
Well, this is kind of like a weak argument, but it's given that the mass is greater, it kind of has more of an impact on the block. So like, imagine a fly hitting a truck on the highway, nothing happens, but a car hitting a truck on the highway, then it's all of a sudden a lot more.
I think that's a good start to it. So what were the two things you had? Hitting a truck, a fly hitting a truck, and a car hitting a truck. So how is the car hitting the truck going to affect the truck differently than the fly?
The car has more inertia.
So it has.
I don't know.
Before we get other ideas, somebody help him finish this thought. We can do it this way. You got an idea, Anthony?
So if it has more mass, it has more momentum. So the momentum at the beginning is like more. So then when you add it, like it'll be like the momentum at the end will be more. So like it'll be a higher velocity. Like your velocity in the beginning will have a bigger impact on your velocity overall because it has more mass.
Okay. Yes, I think you got the first part down. I think you haven't quite finished it. Hold that thought for 1 second. So to finish it, Adam's thought. So I think the one piece you're missing there is that the truck is going to, the car hitting the truck will cause a larger change in velocity in the truck. Right? Because maybe that's not the best way to go about it. All right. So I think I liked Anthony's start for it, is that a dart with more mass is going to have more momentum, which is then going to translate to more velocity after the collision, right? So then what's the next step, Johnny?
So the kinetic energy increase.
There you go. So that means you have more kinetic energy, which is going to get you up higher, right? Follow? So again, did anybody look at the grading on that? What was this 1 point or 2 points? Did you look at it, Molly?
Oh, I'm sorry. Do you want the answer to taking or?
Sure. Yeah. What does it say?
So like similarly worded.
See, it's hard to say, isn't it?
So the greater, the more massive the dart is, it would cause the speed after collision to increase it or increase it less.
Gotcha. Yeah, actually, I just realized I pasted it in here. Let's see. Selecting increase for a correct justification. Okay, so you get 1 point for saying increase and then a point for saying why. Example, a more massive dart would cause the speed after the collision with the block to increase. A greater speed after the collision causes the block to reach a greater height, and thus the angle would increase. Yeah. Okay, so sounds like they're not too fussy about that. All right. And then how's that going to affect? Oh, yeah.
Can I just justify it by doubling the mass and finding out the new height?
Absolutely. Like just redoing the calculation? Yeah. I think that's more work than you need to go to, but you can do that, yes. Okay. Roman numeral 2, how's it going to affect, what does it ask for? The time, I think? It's the same, right? Because what determines the period? Length. And that hasn't changed. That's all I got to say. Cool? All right. Any problems with whatever that was, number 2? All right. Number 3 was a little tough, yeah? Some calculus? Okay. So you're given this rod, right? It says a uniform, emphasis on the word uniform, we'll talk in a minute about why that's important. A uniform thin rod of length L and mass M is allowed to pivot about its end as shown in the figure above. Using integral calculus, derive the rotational inertia for the rod around its end and show that it's mL squared over 3. So, we definitely didn't do many of these. I think we may have done one of these. I remember discussing it when we got to this chunk, and I said this is very similar to how you find the center of mass. All right? So really quickly, I don't know if you guys remember, this is somewhat related, but will hopefully help you kind of put things in context. So when we did those center of mass problems, what we did was we said, all right, well, the position of an object's center of mass is the sum of the position of particle I times the mass of particle I divided by the total of all the masses, right? Okay? But sometimes we had to solve that using calculus, right? And so when that happened, if it wasn't like a finite number of particles and you couldn't just add them up, we had to use calc. And so it boiled down to integrating the position with respect to mass over the integral of dm. So do you guys remember the weirdness that occurred here? You can't integrate x with respect to mass. That doesn't sort of make sense, right? So do you guys remember what the trick was that we had to use? Sure, pick up Patrick. Yeah, so most of the problems gave you an equation for the linear density, where they said that an object has a linear density of, and it was usually like, what, like k, some constant k times x or something like that, right? If I remember right. Okay? And then you said, oh, and that linear density is the same as the amount of mass per unit length, right? And then you could do some substitutions, right? Okay? This is going to be similar, but actually easier, I think. All right? So when I read through the problem, I tried to emphasize the fact that it tells you that the rod is uniform. Why is that so important? What do we mean when we say that something is uniform? The density is uniform. So suppose I cut that rod up into 1 centimeter lengths. What's going to be true about every 1 centimeter? Same mass, right? Okay? So, that's going to become important here in just a minute. All right, so here's how we're going to do this. It says, using integral calculus, derive the rotational inertia for the rod around its end shown. So, incidentally, I discovered, I was helping somebody with this during the tutorial, I discovered that the equation for, the calculus equation that they want for this is on the equation sheet. All right, and it gives you this. On your equation sheet, it says I is the sum of mr squared, which is equal to the integral of r squared with respect to the mass. So that was the integral you had to take to solve it. That's on the given equation sheet. So let me pause there for a minute. Do you guys, so this expression here is the rotational inertia of a point particle, right? And this is saying, let's add up all the point particles. Okay? But here we've got a virtually, I mean, it's not technically infinite, but we've got a crap load of particles in this thing, right? So we don't want to add up all those particles individually, so we integrate. All right? And so what we're going to do is we're going to integrate r squared with respect to the mass at that point. Follow? It is weird. I always have a tough time sort of processing what it means to integrate with respect to mass. It just feels weird. So I don't have a great, I wish I had a better way to lend some insight to what that means. At this point, it's just kind of trust your math. Yeah, and remember it, right. Okay, so the problem, once again, is I can't integrate r squared with respect to m. It doesn't make sense. So I need to somehow change my dm to dr, right? So here's the trick, you guys. The trick is, what I want to do is I need to come up with an expression for dm dr so that I can solve for dr. So, again, idea? Yes, so that's what lambda is. So for those problems, lambda is the linear density, right? It's the mass per unit length. And when we did it with center of mass, it wasn't constant, right? But this time it is constant. So we actually can come up with an expression for what lambda is. Thoughts? It's just m divided by L, right? If it's uniform, isn't the linear density just going to be the total mass divided by the total length? Follow? Oh, so that means that dm is the same as mass over length dr. Follow? So, here's what we just decided. We decided that dm was m over L dr, and we decided that I was the integral of r squared dm, right? Now, when you integrate, technically speaking, when you integrate with respect to mass, you want to integrate from a mass of 0 until you get to the total mass. So this is a capital M, this is a little m. Follow? All right, so what am I going to do now? Substitute, right? Replace the dm with m over L dr. So this becomes the integral of r squared times m over L dr. So I'm no longer integrating with respect to mass. Now I'm integrating with respect to radius. So if this is my radius axis, what do I want my radius to run from?
0 to L.
From 0 to L. Let me pause there for a minute. Did I lose anybody? This is like real deal calculus. This is not easy. It is, yeah. All right, are we good? All right, so what can I do with that m over L? Pull it out, it's a constant, right? M and L are fixed numbers in this problem, right? The rod has a mass of m, a length of L. So this becomes m over L times the integral from 0 to L of r squared dr. Follow? All right, we are almost done. Now that we've got this set up, I think we're through the worst of it. What's the integral of r squared dr? R cubed over 3. Oh, we just got our over 3. We got our 1/3, didn't we? I'm excited. Maybe we're doing something right here. Right? So we got m over L times, we just decided it was r cubed over 3, and then we had to evaluate it between 0 and L, right? Okay, well, let's see. When I plug L in, I'm going to get L cubed over 3 minus 0. Oh. Capiche? All right, the minus 0 goes away. L and L cubed. Oh, we got it. M L squared over 3. Giant smiley face because we kick ass. So that, yeah. And that was like that problem yesterday when it was like, this is more math than physics. Comes up. It seems to me like probably 3/4 of the problems, the 3/4 of the tests will have one very calculus-y problem like this. So, problems with it? All right. So from here, I think the rest of the problem wasn't too bad, if I remember right. Part D, derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of ML and physical constants. So what is position B? Is that at the very bottom of the swing? Yeah, down here. And we're looking for the velocity of the free end. So we're looking for V, right? So, thoughts about how to solve this, you guys? Sure. Zach, I haven't talked to you yet today. What do you got?
Yeah, so
Sorry, Justin.
I set the rotational kinetic energy at the bottom equal to the initial gravitation.
Love it. So what you're telling me is that at the bottom, down here, we're going to have rotational kinetic energy, and at the top, we're going to have gravitational potential energy, yes? What's the GPE at the bottom then?
set it to 0.
Set it to 0. So that means that my height is changing by a factor of,
L over 2.
good. Why is it L over 2, you guys?
Center mass.
Because you treat it from the center of mass. It's a uniform rod. So the center of mass is going from here to here. It's going down by a distance of L over 2, right? Okay? So let's see, my RKE at the bottom is going to be 1/2 I times omega squared. My GPE at the top is mgl over 2. And I want to set those two things equal to each other. Good? All right, so let's see. 1/2 I omega squared equals mgl over 2. All right, we just figured out that I was 1/3 ml squared. Now, there's a couple ways you could do this, you guys. I guess my thinking is this. We're not, what variable are we looking for, you guys? The velocity of this end point down here, right? So we want the linear velocity, the tangential velocity of that point, right? So I gotta find a way to put that into the equation. Oh, but v is just omega over r, right? What's my r? I guess I should have.
Times R.
Oh, yeah, sorry. I wanted to do this. Omega is v over, and what's r, you guys? L, right? Thank you for correcting me then. Everybody good? So from here, I think it's just kind of plug and chug, right? Let's see, what are we going to get here? So I've got 1/2. My I is 1/3 ml squared. My omega is v over L. Don't forget to square it. That equals mgl over 2. Good? All set?
Yep.
Cool. Any problems or anything? Okay, cool. Have a good weekend. I'll see you sometime. Cool. All right, so let's see. What cancels here? Let's see. The 1/2 and the divided by 2 cancels. The m's are going to cancel. This L squared cancels this L squared. So it looks like I'm left with, what, v squared over 3 equals GL, right? Oh. I don't know if that's you, but whoever's singing. Lovely, but not right now. Everybody good on that? Guys in back? Everybody good? All right. So that was, I don't know, what was that, part B? All right. So part C. I hope you guys are starting to see some patterns here. These questions are totally similar, right? All right. So we just found this. V equals the root of 3GL, right? Okay? So it says an experiment is designed to test the validity of this. A student uses rods of various lengths that have a uniform mass distribution. The student releases each of the rods from the horizontal position A and uses photogates to measure the velocity at the bottom. The data is recorded below. C, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration of gravity due to G. So, how do I make this so that it's a linear equation? What would be a good place to start? I will turn this into a linear equation. Is it linear right now? No, because you got a square root, right? So what should I do? Square it. Okay, so let's see. V squared equals 3GL. All right? And I need to get this in the form y equals mx plus b, or b is 0, right? So I'm looking at this. I'm thinking, well, if I make this y equals, let's see, mx. So you can either make m3g and plot L, right? Or make mg and plot 3L. Follow? So to me, this is probably easier. Let's just make our slope be equal to 3g and make x be L. Does that make sense, you guys?
Why couldn't we just have y be d and then x be root L? And then be root 3.
Oh, I guess you could do that. That would work. Yeah, okay, that works. Yeah, I'm good with that. All right, everybody good? So there's a few ways of doing it. So doing it this way, your horizontal axis is going to be L, your vertical axis is going to be v squared. Plug in your numbers, plot your data points, find your slope. Once you find your slope, you go, oh, well, my slope is 3g, so that means g is whatever my slope was divided by 3, and you're done. Cool? Is that enough? Do I need to run through the calculations? Okay, cool. All right. And then finally, last problem says, using your straight line, we just did that. Roman numeral 2, describe 2 ways in which the effects of air resistance could be reduced. I balked at this one when I read it. I was like, what? So the experiment is this. So you've got a rod. Yeah, and I was surprised they accepted one of the answers that I was like, can they really do that? But they took it. So here's the experiment, right? And we're finding the velocity at the bottom, right?
Yes.
So did anybody come up with some solutions? How could we decrease the air resistance? So give me one, Rothy. Do it in a vacuum. Yes, weirdly they will accept that. I was surprised because that's not really a realistic, right? Not a very realistic one, but they did accept it. It was on them. What else? Carla, give me another one.
Make the object more aerodynamic.
Cool. How could you make it more aerodynamic? I know it didn't ask,
A
but
smaller surface area, like piercing the air.
good. Smaller surface area piercing the air. Very good. What else we got? Bathroom. Come on. Margaret, what do you got?
Do it at a higher altitude.
Ooh, why would higher altitude? Ooh, this is
The air
neat.
is thinner.
Why would higher altitude matter?
Because it's like
Less air. That's sneaky. Have you come up with anything else? What else, you guys? Vacuum, we said that. We're missing some important ones, you guys. Why? Oh, Josh just said one. What do you got, Josh? Why would shortening the rod matter?
because the inertia is closer to the center point.
Think about the ducks, you guys. Why would a shorter rod? What do you got, Johnny?
There's more velocity on the end, so it would be.
Right, remember, the faster you're going, the more air resistance there is, right? So the longer the rod is, the faster the end is going to be going, and therefore the more air resistance you've got. So shorter rods would have less air resistance. That's a really good one. Okay? I can think of 2 others. Why, you said that before, why does the temperature matter? Okay, so another way of decreasing. Yeah, I guess so. I don't know.
That's not what's there.
That's this is, my chemistry is a little sketchy here. I know PV equals nRT, but what are the conditions on that? Doesn't it have to be a fixed?
Doesn't really matter.
PV equals MRT has all the variables in it, so it's all, it doesn't matter, it's not at a set temperature, you can put in any number.
Right, but that's what I'm so is that true though, that if in this room I was to make it hotter, does that change the air pressure? There's still the same number of air molecules.
Yeah, because remember he lowered the pressure and then it was like
Alright, I think you would have to justify that. Alright, anyway, there are 2 more physics-y, less chemistry-y, because I don't know chemistry, 2 other physics-y explanations that are solid. Yeah, Robbie?
So hear me out. So if you live on a different planet where acceleration is different, it will not reach as great of a velocity, and therefore there will be less air resistance.
I don't think that works, because we're trying to find the acceleration of gravity. How come? how come if I drop a piece of paper and I drop a book, the paper floats more slowly?
Less dense.
Less dense. So you could increase the density of the rod, right? Well, how would you do it? How would you create a vacuum? And then the other example, and you guys, I'm tired of this battle. You guys are, I know you're seniors, I know you're excited. But like our test is in a week. Chill. All right, so the other reason I came up with it wasn't on the thing and I was surprised is you could, instead of releasing it from a high angle like this, couldn't you release it from a lower angle? What would that accomplish? Less speed, right? Right? Because up here, it's going to have more time to accelerate and gain speed. Whereas if you drop it from like 45 degrees instead of 90 degrees, it has less time to gain speed, right? But you can still do all the calculations, right? Make sense? All right. Any other thoughts about this? Okay, cool. Do you guys want me to go back and do number 1 real fast?
I assume that
You know-
all the people grading them are pretty competent.
Yes, yeah, totally. Yeah, I mean, they're...
So they will understand the gravity of my
Well,
watch.
Jack, the one just set the bottom of the ramp to be a distance of D.
I don't know.
No one knows.
All right, guys. All right, so for this one, yeah, I agree exactly. Justin just commented, why do they set the bottom of the ramp as a position of D? That is the worst thing about this problem. It totally messes things up. For whatever reason, they've decided to call this a position of 0. Now, there is a legitimate reason.
So you can get it wrong.
So you can get it wrong. No, there's another like laboratory experiment setup.
That's where the sensor is.
What? Because that's where the sensor
You said that
is.
4 times, Sebo. I said that. I agree.
Okay, good job, Sebo. Frothy, get your game together, dude. You're sucking it up. All right. All right. Yeah, that's where the sensor is. You're measuring the distance from the sensor. All right. So the object begins at a position D units away from our motion sensor. All right. So.
Because then you'll smash it.
All right. So moving on. Part A says determine the acceleration of the block. So. Does it tell us that friction is negligible?
Yes.
Yes, negligible friction, right there. Okay, so the idea is, as the block is sliding up the ramp this way, what's the only force acting on it? Fg sine theta. Well, that's the only force that's going to affect its motion, right? So you just go, oh, well, net force is net force, right? So mass times acceleration equals Fg sine theta. Ma, oops, try that again. Ma equals mg sine theta. Cancel your m's. A is g sine theta. Now, be careful, that's wrong. Why? Oh wait, oh no, it's not. It is right, it is right. Why did I pause? What was I checking? Signs, right? Our number line is set up such that any motion this way is positive. The acceleration of gravity is in that direction, so that is a positive acceleration. So our acceleration here should be positive g sine theta. Yes.
So I know that they're pretty stuck on
I got you.
showing your work, but like, would it have been alright if you just went straight to g sine theta?
I don't know the answer to that. Let's take a look at the.
Probably the same point for saying axis.
I'm a big fan of net force equals net force, and they're going to be grading this, and they're going to be like, how is this teacher that's telling me to write net force equals net force? It does say that you get a point for using Newton's second law. So, yeah, I think you can't skip it.
It's 1 over.
Oh!
Just get the answer right. Just written down the units. There's no way you could say.
Yep, you're right. Yeah, you're right. You're right, I agree. Sebo and then Brothy.
I didn't have a hand up.
You totally had your hand up.
Sebo, you're a liar.
All right, Brothy, what do you got?
You're a liar. So, say we decided to set the direction to the right negative and label that clearly because D is just a constant that we set, a variable, so that can be negative.
They tell you specifically
No, we just said it was a distance.
A motion sensor aimed down the ramp is mounted at the top of the incline, so the positive direction is down the ramp.
I didn't read it carefully.
Yeah, he really sucks.
All right. Roman numeral 2, determine an expression for the velocity v of the block. So, what does it tell us here? Let's see. It tells us it's projected up the ramp with initial velocity v naught, right? Notice that v naught is the magnitude of the initial velocity. So, determine an expression for the velocity of the block. Velocity at time t is vi plus at, right? So, what's my initial velocity? Negative v naught. Thank you, stupid test writers. Cool? Gotta watch those signs. They're out to get ya. Roman numeral 3, determine an expression for the position of the block. So, I guess probably the easiest way, I thought this. Right? So remember, delta x is our position at time t minus our initial position, right? Follow? So, add the x naught to both sides. Incidentally, I think this equation here is on the equation sheet with that stupid plus x naught at the end. So you get this, x of t is 1/2 g sine theta t squared minus VOT plus d. Right, that's like, yeah, exactly. Like if you were doing integration, that would be your plus c, exactly. Yeah, so if you solved that by integration, it works, but you got to solve for c and c of t. And don't use calculus unless you have to. Cool? Any problems? All right, B, derive an expression for the position x min of the block when it's closest to the motion sensor. Express your answer in terms of blah, 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 blah. There's a gazillion ways to do this. Basically what you need to do is you need to solve for the time when the velocity is 0, right? And then plug that time back into here. Cool? I guess you also, oh, here's an even easier way to do it. So 2 g sine theta delta x. So I want final position, so x min minus d equals v naught squared. No, it's negative v naught squared. And then solve that for x min. That would work too, I guess. I don't know, whatever. Anyway, there's a few ways of doing that one. Cool? All right. All right, part C had these graphs. On the axes below, sketch the graphs, blah, 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 blah. So, position time graph. At time 0, what's my position? Let me do this. So, at time 0, my position is D. The minimum position achieves, we just found, x min. So your graph should look like this.
Should it not touch the x-axis?
That's correct, because it never gets to a position of 0, presumably. It says it doesn't reach the sensor, so yeah, so it never gets to 0. Good? All right. What's my starting velocity? Negative v naught, right? And then the acceleration is positive. So some of it is that I wasn't great about vector notation. They didn't put a little arrow over the top of the V naught. So theoretically, this time should correspond to this time.
Yes.
I would make a note of that. I don't know that it explicitly says it, but I would, so call this like T min. Cool?
Yes.
All right, and then what's my acceleration graph going to look like, you guys?
Horizontal line.
Horizontal line at g sine theta. Positive. Cool?
Yes.
Alrighty. Shoot, we do not have time to do first Stevie. I'll pick those up one day next week if you guys need me to. The solutions are on the thing. So Monday, you've got the 2012 stuff due. Hypothetically, if I was to do like an hour and a half review after school one night next week and or next weekend, well, Sunday's Mother's Day, but if I was to do either of those things, would people attend? All right, I'm going to send out, before the end of the day, I'll send out a survey to find out what times and dates work best for people, and I'll try to pick one day after school and sometime Saturday. Okay?
Cookie day.
What's that?
Cookie day.
One more time. Cookie day.
Next week I'm gonna bring in cookies and sell them all week. My cookies are way better. So.
You all set? Any problems, questions, concerns? Oh shoot, I did tell you about the things. What's that?
Is that you, Philip?
It's a Twin Peaks reference. So, there's the Twin Peaks TV show from the 90s. And then they released, a couple years later, they released a movie called Fire Walk With Me, which is explaining what happened leading up to the TV show.
Okay, so
And David Bowie is in it. And he plays a character named Philip Jeffries. He is a special agent, and then bad things happen to him, and he disappears, and nobody knows where he went. So then he is supposed to be in the reboot of Twin Peaks, but he can't be because he's dead. And because it's David Lynch said, well, we'll just say that he turned into this giant mechanical steam kettle thing.
So now he's forever lived as a steam kettle.
The embodiment of a steam kettle.
Exactly.
That's all I strive to be in life.
The literal embodiment of a steam kettle.
Wait,
Sorry?
A master.
Oh, yeah. There's scales over there on the table over there. A master, you know. You are welcome. How are you?
I'm good. Test.
Oh, okay.
Am I gonna need a calculator or no?
Yeah, probably. All right, let's see. You're in 6th hour. You're in beginning of AD.
Yeah, it's in.
See you guys. Frothy, I didn't really think you were sucking it up today. You're good.
Someone just stole my answers.
I know, because it's being bad.
You stole it, right?
I might be. I meant to use credit detector. DeGrand, no, Downey. Oh, DE comes before DI. There it is. Alright, so that's that. I'm going to turn this off so that nobody has to hear me using potty language. Yes, absolutely.